In this function, we'll talk about the limits of some special functions that are continuous over their domains, as well as doing a couple examples together. So let's start, as before, by just remembering our definition. If f of x is a function and c is a constant, the limit of f of x is L as x approaches c if, as x gets arbitrarily close to c, but not necessarily equal to c, the output of f of x gets as close to L as we want. And in this case, we write that the limit as x approaches c of f of x is equal to L. So previously, we saw that for any polynomial f of x and for any real number c, the limit as x approaches c of that polynomial f of x is just equal to the value of the polynomial at that point. In other words, we can just plug in. So we can just plug in our value. And remember, a polynomial is anything of the form where there are constants like 31.6 times x to some non-negative integer power like 23 minus pi times x to the fifth plus e to the seventh. That would be a polynomial. We have constants in front of x to non-negative integer powers. So that's an example of a polynomial. Okay. And we also saw that for any rational function r of x is something of the form p of x over q of x, where p of x and q of x are both polynomials. So a rational function is a polynomial over a polynomial. For any such rational function, the limit as x goes to any number c of p of x over q of x is equal to just plugging in the value again, p of c over q of c, for q of c not equal to 0, for q of c not equal to 0. So these are both functions that we'd say behave nicely on their domains, that the limit exists and is equal to the function value at that point for any value for any point within its domain. Recall that the domain of a function is the set of all input values for which the function is defined. So for example, the domain of polynomial functions is all real numbers. When we say all real numbers, what we mean is all numbers on the real number line, so 0, and any real number that we could put in between positive and negative infinity, not including positive and negative infinity, so, negative 24.638 is a real number, for example. And so you can denote the set of all real numbers in different ways. One way is to denote it as like a typeface R, like that. Another way to say the set of all real numbers is negative infinity to infinity. That's an open interval from negative infinity up to positive infinity. So that's the domain of a polynomial function. The domain of a rational function is the set of all values x such that the denominator is non-zero. So the domain of the rational function r of x equals p of x over q of x is the set x in negative infinity to positive infinity such that q of x is not equal to 0. So that would be the domain of r of x. And as one last example here, the domain of sine of x is all real numbers. So the domain of sine of x is all real numbers, and we know what sine of x looks like. So it's a function that oscillates between positive 1 and negative 1 in a nice even way. And it starts at 0 at the origin, and at multiples of pi over 2, it's either positive 1 or negative 1. This is 3 pi over 2, and at multiples of pi, it's always 0. And so on. and it continues that way forever and ever. But in terms of the domain is all real numbers. We'll write the domain as negative infinity up to positive infinity, all real numbers, because sine of x is defined for any value of x. So to review this idea a little bit, why don't you think about those four functions below and try to give their domains. So the functions f of x equals cosine of x, g of x equals square root of x, h of x equals tangent of x, and t of x equals natural log of x. So think about the domains of those functions just for a moment. So that is, we're thinking about what are the input values for which the function is defined. So pause and try thinking about that just for a moment. Okay, f of x equals cosine of x. So that's a function that's very similar to sine of x. It's just shifted over pi over 2 units. So instead of starting at 0 at x equals 0, it starts at 1, and then we have this oscillating function from there on out, and that wave just continues going. Here we have an output of 1 when x is equal to 0, an output of 0 when x equals pi over 2, an output of negative 1 when x is equal to pi, and so on. And so that just continues in that same pattern forever and ever. And so and that tells us that the domain of cosine of x is also all real numbers. So we could either write negative infinity up to positive infinity, or we could write the symbol for all real numbers, that sort of r with an extra line. Okay. How about g of x equals square root of x? Well, what numbers have square roots? For example, the square root of 1 is 1, the square root of 4 is 2, the square root of 0 is 0, and the square root function looks kind of like that. But we know that square root of x does not exist, is not defined for x less than 0, or, we could define it as the imaginary numbers. Square root of negative 1 is I. So if we're thinking about complex numbers or imaginary numbers, we could say it exists, but our calculus course at this point is completely just in the world of real numbers. So in our course, square root of x does not exist for x less than 0. If you took a course like complex analysis, then we would be considering what happens in this larger space of complex numbers. But in any case, the domain here for this function g of x equals square root of x is the closed interval 0 up to infinity. So 0 less than or equal to x, which is less than infinity. That's the domain of that function. Okay, how about h of x equals tangent of x? So tangent of x, you may remember tangent of x is equal to sine of x over cosine of x. And so this is kind of like our rational functions. This is going to be defined when cosine of x is not equal to 0. So we can look back up and see when is cosine of x equal to 0. Cosine of x was equal to 0 at basically values of pi over 2. So when x is not equal to k pi over 2 for k an odd integer. So when was cosine equal to 0? It was equal to 0 for pi over 2, for 3 pi over 2, for 5 pi over 2, and so on. So that is going to be our domain. So our domain for tangent of x is all places where cosine of x is not equal to 0, or all real numbers x such that x is not equal to k pi over 2 for k odd. That's our domain. And we can also do a quick sketch of what tangent looks like. So basically we're going to have an asymptote at every pi over 2 times an odd integer. And we've got sine of 0 is 0, so that is tangent of 0 is 0. And then we've got this, we're going to end up with a vertical asymptote at each of those values because it's some constant divided by 0, so 1 or negative 1 divided by 0. So it's going to look kind of like that, just a repeated little guy doing disco here, forever and ever and ever. Okay, so our last function is t of x equals natural log of x. So you may remember that natural log of x is the inverse of e to the x. So in other words, natural log of x is equal to y if and only if e to the yth power gives us x. So let's think about what values x can take on. So it might help us to think about the function e to the x, or e to the, let's just say t, e to the t. E to the t is going to look kind of like this. So e to the 0 is 1, just as anything to the 0 is 1. E to the 1 is going to be e. E to the 2 is going to be e squared, something close to 8, and so on. So it's getting really exponentially large. It's an exponential function. But when we think about e to the negative 1, remember that negatives flip the fraction, so that's 1 over e. It's getting smaller. E to the negative 2 is 1 over e squared. It's getting smaller still. And so this is getting close to 0, but never quite reaching it. The main point here is that e to the y is always greater than 0. It's never less than 0. And so that tells us that what values can x take on? This x value can only be greater than 0. So the domain of natural log of x is all x values strictly larger than 0. In other words, it's the open interval from 0 to positive infinity. And if we wanted to draw the graph of the function of natural log of x, because those are inverse functions, we could reflect across the line y equals x to draw natural log of x. So this would reflect across that line and be a function that looks kind of like that. So this is natural log of t. Okay, so now that we've reviewed a little bit about the domains, here's our theorem about limits for special functions that are continuous over their domains. If c is a real number in the domain of the given function and n is a positive integer, then all of these limits hold. So all of these functions that we might not use quite as often have limits where we can just plug in. So for any c in domain for these functions, the limit as x approaches c of f of x is just f of c. We can just plug in. Okay, so with the statement of that theorem in mind, why don't you try the following examples? So find the following limits, and you can pause the video and try those out. Okay, so our first example is the limit as x approaches pi over 2 of 3 cosine of x minus 2x. We can remind ourselves what cosine looks like. It's this function that oscillates between 1 and negative 1, and we know that cosine starts at 1, and at each multiple of odd pi over 2's, cosine is 0. So we know that cosine of pi over 2 is 0. And so these are both functions that are continuous over all real numbers, 3 cosine of x and 2x. So we can just simply plug in the value. This is 3 cosine of pi over 2 minus 2 times pi over 2. And so this is 3 times 0 minus 2 times pi over 2 is just pi. The 2's cancel out. And so we get negative pi is the limit of this function as x approaches pi over 2. Now, second example, limit as x approaches 3 of 2 to the x squared minus 4. We saw that exponential functions also just approach, we can just plug in the values for as well. So this is going to be 2 to the 3 squared minus 4. That's 2 to the 3 squared is 9 minus 4. That's 2 to the 5th. So 2 to the first is 2 to the first is 2, 4, 8, 16, 32. So that's 32 is 2 to the 5th, and that is our solution. And finally, limit as x goes to pi over 2 of cosecant of x. So remember that cosecant of x is 1 over sine of x. So we could either think about cosine of x as a function of itself, or we could just sort of think about sine of x and what we know about sine of x in order to answer this question. So we know that sine x at, this is pi over 2, has an output of 1. At pi over 4 has an output of square root of 2 over 2. So sine of pi over 4 is square root of 2 over 2. And that tells us that, well, first of all, cosecant of x is defined here. So so this is not equal to 1 over 0. So pi over 4 is in the domain of cosecant of x. And this is one of the functions above for which, for any point in the domain, we can just plug in the value as x approaches c to find the limit. So this is just cosecant of pi over 4, just plugging in the value, and that is equal to 1 over sine of pi over 4, and so that's 1 over square root of 2 over 2, and so we can just flip that fraction. That's equal to 2 over the square root of 2, and you can leave it as that. It's fine to leave square roots in the bottom, or if you prefer, if you want to take the square root out of the bottom, you can multiply the top and bottom by square root of 2 to get 2 square roots of 2 over 2, and either of those is fine.